Alright, hey guys, what's going on? So today we're going to be talking about covariant and contravariant transformations. Now this is going to be a relatively short video, I think. Again, if you like this kind of content, hit subscribe, hit like. You can go onto my Patreon page too, where more content will be coming up there as well. I realize I'm putting less stuff on my Patreon page right now and more stuff on my YouTube channel just to get things up and started on the YouTube channel first. So I'm a little bit more focused on the channel right now. Anyways, let's get right into this. So we're going to be talking about covariant and contravariant transformations, specifically of basis vectors. So I want to look at this a little bit in a little bit of a way that's probably not a way that you've been exposed to before. And if you have, then great, this will be a breeze to go through. If not, I want to make this really, really simple. And the way I'm going to make it simple is really by looking at this picture right here. So first, we have this picture right here where we're looking at what we've called before a manifold, right? So this manifold is really just a mathematical sort of description of space and time, right? So it's we can think of it again as like this three-dimensional space, right? Or four-dimensional space-time, where you have space and time in one cohesive unit, right? But for simplicity, we just can reduce this down to 2 dimensions for right now, keeping in mind that we're talking about actually 4, right? The 3 spatial dimensions and the 1 temporal. And we want to look at this picture here where we have, again, the manifold in which we live, right? This is space and time. And at each point in space and time, we could call these moments, right? At each moment in space-time, we have this orthogonal system of basis vectors at each point in space and in time. And these can evolve, right? These orthogonal systems can evolve in space, and they can also evolve in time. And we'll take a look at that later. But right now, we kind of just want to look at this picture where we have, again, space, time, and at each point in space-time, we have these little coordinate systems that we can draw up, right? So if you're in if you're at this location, say, this is what your coordinate system looks like. And so any vector that you perceive at that point is going to be within the framework or within the frame of this coordinate frame, say at point A. Okay, so we can call this point A and this point B. This over here can be C and so forth, C and D, and all the way up to infinity, right? There's an infinite number of points in space as far as we know, or it could be finite depending on the expansion of the universe and so forth, but I digress. Anyways, when we look at this picture, we want to understand that there's 3 things here, and I've color-coded them for a reason. There's 3 things here that we want to keep track of, right? There's the underlying coordinate system, or not coordinate system, but there's the underlying manifold, right? So we call this sort of the coordinates of the manifold, right? So you have your x, your y, your z, and your t, and we subscript these with 1, 2, and 3, 4, 5, and 6, and so forth, starting at 0, where this is typically the, I'll write this out, this is typically your t, x, y, and so forth. And then we have these basis vectors, right? We want to also keep track of. So we need to keep track of coordinates, right here, and we also need to keep track of our basis vectors, right? So our basis vectors, again, these are these red guys, right? So E, say, in the x direction, then we have E in the y direction, and then we have E in the z direction. We can imagine there's an E in the t direction also, but one that we can't see. And then I'll just erase that for right now. And then we have the vector components themselves, right? So when we write out the vector, say this is R, our vector R has components, right? It has Rx, has RY, and it has RZ, right? These are the components that make up R. And if we want to be a little bit more specific, we have our basis vectors as well. And so that's our base. So these green guys, right? These green guys here, we also need to keep track of these, right? So we have our underlying coordinate system, we have our basis vectors we need to keep track of, and we have our vector components that we need to keep track of. Now this is something of a daunting task, but it becomes even more daunting when we evolve to this picture, right? So in the previous video, we've just talked about covectors, how these things are fundamentally different than vectors themselves. And what that means is that there's even more things to keep track of, right? So we go to this list, right? We have our coordinates we need to keep track of. This is the underlying coordinate space, or our manifold space. Then we have our contravariant basis, right? So those would be these guys. Then we have a covariant basis, which would be these guys. We talked about these earlier. Then we have a contravariant components of vectors, right? So that we talked about force last time. We could have other different types of vectors though that are contravariant or covariant. And then we have, again, covariant components of vectors in the context of last time we talked about the electric field as being a good example. Right? That's why I have F and E, just to keep us sort of within the context of this playlist and sort of also within the context of a real life example. Anyways, this is 5 things we need to keep track of now. So the list is getting bigger. Now you can imagine, what about tensors, right? We haven't really talked about tensors yet, but tensors are also fundamentally different objects. We are going to want to somehow find a way to minimize the amount of things we need to keep track of. And this is my way of thinking about general relativity, right? In a nutshell, we need to keep track of a lot of independent variables. And the way we're going to do that is we're going to come to a realization, right? So what I say here, wouldn't it be nice if we could keep track of less, right? This is the realization we're going to make. Right, so I put exclamation marks here because this is very, very important. We understand that we have an underlying manifold, right? So here's our underlying manifold again. It's this black. Now at each point in the manifold, or at each point in space and time, at each point in space-time, we could have, say, a vector space, or a vector field, right? So a vector field is, if you've taken calculus 3, I believe in calculus 3 you come across vector fields. You could take, if you visually think about what a vector field is is something that, or it's not something, but we have these vectors that are fundamentally dependent on where they are with respect to space and time, right? And these vector fields can move in different ways. That means they are functions not just of space, but they're also functions of time. Each vector, each point is a function of space and time. So we write our vector at some particular point like this. And when we come to this, when we see that we have a vector field where each vector is dependent on the underlying manifold, then we might suggest the following, that our contravariant basis be defined in this way: the derivative of a vector at that point, right? What does this do, right? This essentially takes our coordinates, these guys right here, right? So go back to my drawing, these guys right here. And see, we went to our contravariant basis. Actually, that was our covariant basis, my bad. We made this connection, right? By saying that this guy here be defined in this way, right? Where the derivative of this vector is the component, is the basis vector at that point, or the derivative. We're essentially equating this with this, right? So this here is on this side of the equation, this here is on this side of the equation. Likewise, this guy here, right? So this guy here those two guys are equated, right? So we've essentially compactified the things we need to keep track of back into three things, right? Because these two guys are getting absorbed into definitions where we have them be defined in a way that is with respect to our coordinate system, our underlying coordinate system. And why can we do this? We can do this because we have a unit of distance on the bottom here. Remember, we talked about how these things changed over, or how they transformed. We had, I'll just write it like this, right? So we have, this is our basis vector. And if we want to evolve our basis, or if we want to transform our basis vector, if we can transform a basis vector like this, and this equals a new basis vector, right? So this here is the transformation. Okay, likewise with this guy, we transform it like this. We want dx like that, right? And this is the transformation. This is also the transformation where we can see here that these two transformations are inverses of one another, right? Because if we take dx mu dx nu dx nu dx mu, well, that equals 1, right? Because, well, not because, but this guy here was right here, and this guy here is right here, right? Those two guys are right there. And we can see that we can essentially do some canceling out. We get 1, right? So the two transformations are inverses of one another, which says that one of these objects, right? So this guy here transforms oppositely to the way this one transforms, right? So we could say that this and this this thing transforms in a covariant way, and this thing transforms in a contravariant way. That is sort of the logic that helps us say that, well, if this transforms in a contravariant way, we can identify it with this basis vector. And so I don't want to trudge on for too long here, but this essentially means that we can think now of really just keeping track of our coordinates, right? So x1, x0, x1, x2, and so forth. And then just our components. F1, and then F2, and so forth. this mean for tensors? Well, that's going to be something of a separate video, because I'm realizing that this is about 15 minutes. I don't want these videos to go on for too long. But this is, again, this is the point that we want to make in this video, which is that we've come to a realization that we can use operators as basis vectors, right? And this is going to be this guy here. This is an operator, right? That this is not a vector. It only becomes a vector when we act on it, when we act on a vector with it, right? Likewise, this guy here, this thing is essentially meaningless unless we have, well, this is actually meaningful, right? So this one here requires an operator, right? This one here is actually a small distance, right? So this thing here is actually a small distance itself. This guy here requires some vector in order to be well-defined. And so that's essentially what we want to get at here when we're talking about the covariant and contravariant transformations of basis vectors. Is essentially we've made a realization that we can use derivatives and small distances to act with respect to our manifold, to act as basis vectors. And with all of that, again, please hit that like and subscribe button if this is kind of content you're interested in, and visit my Patreon page as well, where I promise things will be coming up. And with that, I will see you guys in the next one. Bye.